Assalamu alaikum. Today we will be discussing the one-dimensional consolidation test. Data obtained from these tests, together with the classification data and knowledge of the soil's loading history, enables estimates to be made of the long-term behavior of foundations under load. For this test, we'll need a few things to begin. The items involved are porous stone and filter papers of large and small sizes. After that, there is the load cell, and then there is the clamping ring, which goes inside the load cell, the loading cap, and then the cutting ring. As you can see, the cutting ring comes in multiple sizes. For this demonstration, however, we will be using this size. Before you begin, what you have to do is you have to measure the internal diameter and the height of the ring, as well as its empty weight. After measuring the internal diameter and height of the ring along with its weight, the soil will be prepared inside the ring. It can be prepared from either an undisturbed or remolded soil sample. Care should be taken to ensure that the top and bottom side of the soil is completely flush with the upper and lower edges of the ring. After this, the soil and the ring will be taken to the weighing balance to be weighed together. When weighing the soil and the ring together, the ring should be placed on its side to ensure that there is no contact between the surface of the soil and the scale, so as to avoid risking the soil sample falling out of the ring. Following this, all the relevant items are assembled within the load cell. First, the large porous stone is placed within the center of the load cell. After this, the large filter paper is taken and then spread smoothly on top of the porous stone. The purpose of the filter paper is to ensure that during the test, when the water is expelled out of the soil during the consolidation process, the soil itself is not washed out along with the water. After this, the cutting ring is fitted inside the clamping ring and then placed within the load cell. The bolts on the top of the clamping ring inside the load cell are then tightened to ensure that the assembly beneath is securely fastened. Once the bolts are tightened, the smaller filter paper is then taken and placed on top of the soil specimen. Both the filter papers and porous stones above and beneath the soil should be pre-moistened to prevent them from absorbing moisture from the soil. Once the filter paper has been smoothly placed over the soil specimen, we take the loading cap, which has a porous stone attached at its bottom, and place it over the soil specimen. After the assembly of the consolidometer load cell is complete, it has to be placed within the loading frame and the loading yoke placed over the loading cap. After placing the load cell in the loading frame, the load cell is filled with water up to the point where the upper porous stone is submerged. This is done to ensure saturation of the soil specimen and to make sure it is consistently maintained throughout the experiment. The assembly of the loading frame is such that the loading hanger is connected to a lever which in turn is connected to the loading yoke, which transfers the magnified load to the loading cap and the soil beneath it. The factor of the lever arm is 11, which means that whatever weight is placed on the hanger multiplies by that factor before being transferred through the lever to the loading cap and the soil beneath it. As such, if we were to take, for example, a weight of 0.5 kilograms and place it on the hanger, that would translate to being 5.5 kilograms of load being applied on the soil. Before each interval of weight is added, first it is ensured that the supporting jack beneath the lever is tightened so that it is in contact with the lever. This is done so that the load is supported by the jack and not applied on the soil directly before we can start recording the necessary data. Now, there are 3 things to keep in mind before starting the test: load, time, and deflection. First, the amount of load that is placed on the hanger. Second, after a plate of load has been placed on the hanger and the support jack is loosened, allowing the magnified load to act on the soil, you have to start a stopwatch at that very moment to note the time that elapses as the load begins to act on the soil. Third, at specified intervals of time, you have to note the reading on the deflection dial gauge, which indicates the amount of settlement the soil has undergone in that period of time under the application of load via the expulsion of water. Before loosening the support jack, the initial reading on the dial gauge is noted. After loosening the jack, you can observe that the needle of the dial gauge begins to move. The difference between the two values of the dial gauge multiplied by the least count of the dial gauge provide the amount of settlement that has taken place. For any load increments applied to the soil, the deflection of the dial gauge is noted at the indicated intervals of time until either the deflection has become constant for multiple intervals or 24 hours have passed. Here is a table that shows the various load increments that are applied on the soil and the time intervals at which you have to note down the dial gauge readings obtained. After the last loading is completed and the maximum settlement due to consolidation has been achieved, we will begin unloading the soil. This is done by reducing the total applied load to 1/4 its current intensity and allowing it to stand for 24 hours. Once the 24 hours are complete, we will note down the new dial gauge reading. This reading will indicate the restoration of height that occurred in the soil after the lightening of the load on top of it. In further steps of reducing the load to 1/4 the applied loading, decrease the loading up to its value at the start of the test, and after 24 hours note down the final dial gauge reading. Then the entire assembly is dismantled and the cutter ring and soil are placed in the oven to determine dry weight. After this, you will commence with your calculations and graphs.